vorgelegt hat, die von Gutachtern und Gutachtern bewertet wurde. Das ist jetzt aber nicht Thema der ersten Phase. Herr Castro wird uns in einer halben Stunde noch zur Zeit, wollte zum Glück ist auch nicht unterschreiben, in einer halben Stunde kurz mal Ihnen allen vorführen, was er gemacht hat, die Highlights darstellen und uns hoffentlich ein bisschen Verständnis dafür vermitteln. Dann schicke ich so ab der dritten Reihe die Damen und Herren raus und wir werden dann versuchen, Herrn Castro nochmal um eine Stunde zu quälen. Ja? Und also dann noch ein paar Fragen zu stellen zur Arbeit, aber auch außerhalb der Arbeit, was sich gerade so ergibt. Das wird im Wesentlichen dann von den Gutachtern gestaltet, wobei die anderen anwesenden Herren, in dem Fall Professores, dann auch natürlich noch die eine oder andere Frage stellen dürfen. Das dürfte dann etwa so eine Stunde dauern und dann dürfen wir eigentlich alles hoffentlich geschafft haben, aber gehen wir davon aus, dass das so der Fall ist. So, dann darf ich Sie jetzt bitten, so eine halbe Stunde uns mal einzuführen in Ihre Problematik, in Ihre Thematik und die Lösungen, die Sie da gefunden haben. Bitte schön.
First of all, I'd like to thank the Chairman for the kind introduction and to say that I had to do this in English. Unfortunately, my German is not good enough to present everything in German. And before I start telling about the main development of the thesis, which is the semi-analytical models for unstiffened composite shells, I will before show where we can find this type of shells in one typical application. So here we have a picture of the Ariane 5 rocket manufactured by Airbus Space and Defense, where we see two unstiffened conical shells and two unstiffened cylindrical shells. And these shells, they have in common one aspect: they are very perfection sensitive, which means for a small geometric perfection, the buckling load or the load carrying capacity will be drastically changed. So you have a huge reduction of the load carrying capacity for any small geometric perfection. And when we are developing models for this type of shells, these models should be able to capture this imperfection sensitivity. So the main focus when you are developing a semi-analytical model for this type of shell is to be able to capture this imperfection sensitivity. And then this takes us to the model requirements. So what should we be able to consider? And first, I already mentioned the geometric imperfections, and here we have an example of a measured geometric pattern given as a courtesy by DLR. And another typical geometric imperfection that we are currently investigating is the one that induced by a perturbation load. So we apply a perturbation load, there will be a geometric imperfection pattern, and this also causes a reduction of the load carrying capacity of this structure. Since most of our activities are related to cross-validation of test results, we must be able to take into account the axial shortening that we verify in our testing conditions as well. And another phenomena that we must be able to capture in these semi-analytical models is the so-called elephant foot effect, which carries this name because of the pattern that we see here. And this pattern happens because when we apply the axial compression, there will be a radial expansion of the shell, and with the edges constrained for normal displacement, we have a high strain concentration close to the edges, and this becomes an important failure mode that the models must be able to capture. Not only in the space industry, but also this is very much investigated in the civil engineering field. And we decided to use the Ritz method, where we approximate the displacement field as shown here. So we have our model, and the coordinate system is illustrated here, and we have three displacement field variables, translational displacement field variables as shown here. One is for the x-axis, we call u. The second one is for the circumferential axis, we call v. And the third one is for the normal axis, we call z. And the displacement field variable is w. So when we use the classical limited plate theory, we can build our displacement field vector as shown here, using the three translational displacement field variables. And when we use the first order shear deformation theory, we have the two rotations of the shell treated as independent variables. So we have two additional independent field variables here. When we use the Ritz method, we work directly with the energy functionals, and therefore we obtain the equilibrium equations in an integral form. We can call this also usually called the weak form. So it means that the equilibrium is not achieved at every point in our domain, but in a global sense we guarantee the equilibrium. Some advantages of the Ritz method. The main advantage, I would say, is that it dispenses the use of differential equations. So we don't have to work with the governing equations of the system. You can work directly with the energy functionals. A second advantage is that we obtain at the end a continuous function describing not only the displacement field but also the strain and stress fields all over the domain, and it's very straightforward to obtain strain, stresses, and displacement outputs all over the domain. But at the same time, we need having a continuous function is one advantage. It may become a big disadvantage of the method, because finding the appropriate set of base functions to describe the displacement field all over the domain it can be a very hard test, depending on your boundary conditions and on your load cases. And this is what I'm going to detail now, how I decided to separate and to find the right set of approximation functions for our problem. Again, we can approximate the displacement field vector by a matrix containing the base functions, so we know the shape, the possible shapes that our displacement may have, but we don't know the amplitudes of these functions building up the full function. And then I propose to separate in three parts the full approximation functions. The first part was designed to capture the axial shortening of the shell. The second part was designed to capture the axisymmetric component of the displacement field. And the third part was designed to capture the two-dimensional components of the displacement field. Now I'm going to detail each one of these. The first part designed to capture the axial shortening. When we have the displacement of the testing machine, called here delta Tm, we will have the displacement of the top edge along the meridional direction described by the delta of the testing machine divided by the cosine of the conical semi-vertex angle. And at the same time, we have a null displacement at the bottom edge. And I found that using a linear function a linear shape function for capturing this axial shortening was already enough, and it gives the same result as in defined element as we are going to see in the next slide. And here is how we build our shape functions for the first part of the approximation field. And here it's showing the first row, it corresponds to the meridional displacement u, the second row for the circumferential displacement v, and the third row for the normal displacement w. Now, moving to the axisymmetric component of the displacement field, it is shown here one example for a cylindrical shell and another example for a conical shell. And I decided to use sine functions to capture this axisymmetric component separated from the two-dimensional component, because I'm not, in the sine functions, they will always give a zero displacement at both edges, and I decided to use the sine function because I'm not willing to capture any axisymmetric displacement component at the edges. And therefore we can use the sine function, and it's computationally cheap to separate the axisymmetric component from the two-dimensional component. Now, the last component of our approximation functions, it can be written in matrix form as shown here. And let's take the third row, which corresponds to the normal displacement, and let's evaluate this component. We have two components for the normal displacement. The first one, the difference between the first and the second one is that in the first one we have a sine function for the circumferential coordinate theta, and in the second one we have a cosine function for theta. And in this way, we obtain a full Fourier series for the circumferential coordinate, and therefore we are able to capture any displacement pattern that depends on the circumferential coordinate. On the other hand, for the meridional coordinate x, I only use a sine function because I'm assuming the normal displacement at both edges will be 0, since it's the condition that is very similar to our testing conditions. And for u and v, I'm using cosine functions instead of sine functions to capture the displacement along the meridional coordinate, which means that I'm not guaranteeing a 0 meridional and circumferential displacement at the edges. So in this way, I'm proposing to use these functions, but how can I use these functions and at the same time achieve one of the typical boundary conditions, that is this first type of simply supported, where we have u, v, and w being 0 at the edges. So how can I use a cosine function and if I want to capture u, v, and w being 0 at the edges? So there is a way we found out how to do it, is to use elastic constraints to penalize the stiffness matrix in such a way that we change the stiffness of the system just at the edges. And this is illustrated here. So we have, without the distributed constraints, the distributed springs, we would obtain a displacement pattern like this. But if we want to guarantee a simple supported with where these displacements at the edges, they are 0, we can add the elastic constraints, and in matrix form it's represented like shown here. So we change the linear stiffness matrix of the system, and in all the linear static, non-linear static, and also in the linear buckling analysis, we can use the modified linear stiffness matrix. Let's give one example. To achieve the first type of simple supported boundary conditions, where we have the 3 translational displacements being 0, we can set the stiffnesses Ku and Kv to infinity, and then it will give us the right behavior. And if we wanted, instead of simple supported, to obtain clamped boundary conditions or fixed boundary conditions, we should work with the rotational stiffness at the edges. So we can switch between simple supported and clamped boundary conditions by changing the rotational stiffness of the system. In practice, we never use an infinity value, but we have to use instead a numerical value which is high enough to produce a rigid behavior, but not too high to go into a numerical instability. So we have to find a numerical value, and in one of our publications, I found out that using 10 powered by 5 Newton per millimeter was already producing a rigid behavior, and even though I'm using 10 powered by 8 in the full implementation, and that shows using double precision for the programming code, it showed to be numerical stable and much higher than the necessary amount to produce a rigid behavior. Another important implementation aspect was how to integrate the linear stiffness matrices for the conical shells. Because the conical shells, they have the radius depending on the meridional coordinate x. And because of this dependency, we run into expressions that are not integrable analytically. So we have to find one way to approximate this. And one way that showed to be computationally efficient was to divide the integration domain as shown mathematically here and as illustrated here, where we have different integration sections, and each section using a constant radius which is taken from the middle of this section. And this way, the computational cost to integrate the linear stiffness matrices for conical shells is linearly depending on the number of sections that you use here. And it was interesting that for shells with constant stiffness properties over the domain, we can use only one term, and it gives a result within an error of 2 and 3%. which is very suitable for optimization tests. So if we need very quick cycle for the analysis, we can use only one section and the results will be within a reasonable tolerance. And talking about the results, we can already show some of the results for linear buckling, for linear static, and also for nonlinear static analysis. Here I'm showing some of the structures that I'm going to discuss. Basically, we have a cylindrical shell which was designed at DLR in 1992 by Dr. Zimmermann. And this structure has a special characteristic. It has a very special laminate, as you see here. And this laminate was designed to generate the highest imperfection sensitivity. And in this way, this structure has become a benchmark case for testing many different methods, not only by me, but by many authors. And I designed another conical shell, just also having a high imperfection sensitivity, not using an advanced procedure as used by Zimmermann, but just to get also a high imperfection sensitivity in order to verify the algorithm. The material properties are shown here, and they correspond to a usual ply with unidirectional fibers. In our results, in many of the results, you will see not the three-dimensional patterns, but you will see open cylinders and open cones. So when you see a rectangle like this, it corresponds to an open cylinder, and when you see a structure like this, it corresponds to an open cone. Starting with the linear buckling results for cylinder Z33, we see here the convergence of the first linear buckling mode, where by increasing the number of terms in our approximation functions using the Ritz method, it quickly approaches the pattern obtained using finite elements. And this is also illustrated in this graph, where we see the linear buckling mode approaching the linear buckling mode from the finite element by increasing the number of terms. And in this case, using both the classical laminated plate theory and the first order shear deformation theory, we approach the same result. But for thicker shells, I would expect that the classical theory would give a higher buckling load than the first order shear deformation theory. Now it's showing in this slide not only the comparison for the first buckling mode, but for higher buckling modes. And here it's up to the 9th buckling mode. We can see a very good correlation using the classical laminated plate theory, or the first order shear deformation theory, or the finite elements. And now an important comparison is the computational efficiency of this method compared to finite elements. And we see in this case the finite element using abacus with the element type S4R, which has a reduced integration for calculating the stiffness matrices. It converges with about 420 elements around the circumference, and using this mesh, it takes about 142 seconds. In the Ritz method, for linear buckling analysis, in this case, it converges with about 20 terms, and it takes about 0.54 seconds. So in this case, it's about 250 times faster. Now, moving from linear buckling analysis to linear static analysis, it is shown here the result, the convergence by using a cylinder, the cylinder Z33, and with an imperfection caused by a perturbation load, and applying axial compression. And then we see how, increasing the number of terms again, we approach the result from the finite element code. And this is illustrated here, where I'm measuring the normal displacement at the point where I apply the perturbation load, and how this displacement changes by increasing the number of terms. And again, we get a good convergence. In this case, the convergence is not obtained with 20 terms, but it's obtained with about 50 terms for a tolerance of 2%. And this is because when we apply perturbation load like this, we have high frequency harmonic functions, so we need more terms to achieve this high frequency. Now let's show a computational comparison for linear static analysis. The finite element code convergence here with only 200 elements around the circumference, and it takes about 7 seconds to run. And with the Ritz method, converging with about 60 terms, it takes 1.32 seconds, and is about 5 times faster. And in this case, another very important load case that we must be able to simulate in our models is when we load the structure with non-symmetric loads. Instead of loading the structure uniformly, we are applying, in this case, a sinusoidal function for the axial load. And this is the result that we obtain using the Ritz method. Here we see the displacement pattern for the displacement field over the meridian, and here is the circumferential displacement field, and here is the normal displacement field. And we see again that the Ritz method is approaching the finite element result very well. And not only from the patterns, but from the minimum and maximum values, we can also check this. And a similar result now for a conical shell, again showing a good correlation between the Ritz method and the finite element result. The last nonlinear results I would like to show is for imperfect shells. And the first set of results is showing here for an imperfect shell carrying imperfection from measurement system. So in this case, we have the original imperfection from ATOS system measured by DLR. And in order to apply this imperfection into the Ritz model, we need a continuous function. And we can use the continuous function given by Arbot in 1968, which is called the half cosine function. And we can fit this function to this measured imperfection for a given precision and then use into the Ritz method. I'm using here precision of 24 M0 and 34 M0, and this is how the continuous imperfection field looks like. It correlates very well with the measured imperfection field. And when we apply this to both the finite element model and also to the Ritz model, we obtain these results, and the continuous line shows the finite element result, and the dots here, they are results using the Ritz method with different accuracies. And we can see that the Ritz method converges to the finite element result by increasing the number of terms. And this is as expected, and so we were very happy with these results. And in the previous slide, here I'm measuring the buckling load for different imperfection amplitudes. So I increase the imperfection amplitude by scaling up and down the imperfection amplitude. And then I can measure how this affects the load carrying capacity of the structure. We already saw that the correlation for buckling load was good, and now here in this case I wanted to see if the displacement pattern correlates also well for both the Ritz model and the finite element result. And in this case I'm stopping the buckling test at the onset of buckling, and then for both the finite element code and the Ritz model I take a picture of both for the three translational displacement fields, and this is how they look like. For the Ritz method, it's shown here, and for Abacus, it's shown here. And we see again that they not only look like each other qualitatively, but also quantitatively. We can see here by the minimum and maximum values. Now let's show a computational cost comparison. In this case, using imperfections from perturbation loads, not from measurement systems. And we see that by increasing the perturbation load that caused the imperfection, the load carrying capacity is reduced. And in this case, we are showing also the computational time for Abacus and for the Ritz model. And we see here that the buckling load is very well predicted by the Ritz model. And in average, we have an error of 1.04%. But the Ritz method has a drawback here, which is it's about 10 times lower. And now you may be curious why, for nonlinear analysis, the Ritz method was so much slower than finite elements. Now I'm going to discuss in the conclusive slides. So going to the conclusions already, the first conclusion is that the semi-analytical methods, they achieved their purpose. They were able to capture the geometric perfection or the perfection sensitivity of the structures. They were able to capture also combined load cases that I'm not showing here due to the time constraints, but you can find in the publications that we wrote. And it can be used for general axial load distributions, not only uniform axial loads, but also for any general load applied to the structure. And also you can use for different boundary conditions. And talking about the computational comparisons, in the current implementation, it's about 2 orders of magnitude faster for linear Buckley analysis. It's about 1 order of magnitude faster for linear static analysis, but it can be 1 order to 2 orders of magnitude slower for nonlinear static analysis. And now let's go into this point, why it's slower. When we are integrating numerically the stiffness matrices of this system, usually we sample some integration points where we are going to evaluate the stiffness matrix of the system. And in finite elements, for each integration point, you have to evaluate only a small region of the stiffness matrix corresponding to the degrees of freedom affecting this integration point. Instead, in the Ritz method, since the degrees of freedom here are the amplitudes of the approximation functions, for each integration point, the full stiffness matrix influences. And therefore, for each integration point, we have to calculate all the stiffness matrix. Whereas in the finite element model, we have to calculate only a small part of the stiffness matrix. And from this observation, I can say that using numerical integration, the Ritz method will always be slower than finite elements. Now, the suggested topics for research. In my case, I'm using a uniform grid for the numerical integration of the nonlinear stiffness matrices. But there are quadrature rules that could drastically improve this numerical integration, and this is one topic for investigation. Another topic is if we are using non-homogeneous laminate properties, it's no longer possible to integrate analytically the stiffness matrices, and therefore you definitely need numerical integration for the Ritz method, even for the linear analysis. In this way, the Ritz method would probably be too hard to handle or non-competitive to use, and there is one, I think, very promising method for this purpose, which is the differential quadrature method. And when you work directly with the governing equations, and for this purpose I would recommend to work with the differential equations. And one promising method is the differential quadrature method. These are the publications related to this thesis that we published. And the first one was submitted to the Thin Walled Structures journal in April, and now it's in the second review. And the second that we wrote was for composite structures. It is about linear buckling analysis, and this was approved. And the third one was also for composite structures using the nonlinear method proposed here for imperfect shells, and this was also approved. And now the last thing I'd like to say, everything that was developed is available online, and if you are interested, you can check this online and contact me if you have any questions. And now we are open for questions, and I'd like to hand back to Mr. Chairman. And thank you for the attention.